Okay. I'm sorry, guys, because these are 3 lectures I give you last week for reviewing online. So today and maybe is Friday, I'm going to go through these 3 lecture notes, and then we will move on to next topic. So I think this is just my opinion. So because the nature of this lecture, we have a lot of figures, the equations to write, right? So I think that will takes a lot of time. If you wish, I can still write these equations on a board, on a whiteboard, or if you think it is better so to save some time, I can just show you on the screen. But I just show you some necessary derivations, calculations on whiteboard. Which one do you prefer, guys? You can see, for example, for this one, if I draw this one, at least 2 minutes apart, right? But however, if I show you here, and you also have my lecture notes already, right? And if you can print out in advance, you can just read all these things. That makes more sense to me. I want to hear your opinion, and you can let me know by next Monday. How does that sound? But today and this Friday, I'm going to go through all these things, and you can just draw down these important points. So this is the energy criteria. So where we are, we talk about this is we are here now, right? Is that right? For lecture 2. So it does not hurt. Let me show you. Okay, so suppose this is a through hole. This is the through hole, and this is through hole. We have the sigma infinite. So this is the infinite plate, and we have the infinite sigma stress sigma, and the thickness of this plate is a b. And so this is a 2a. The crack length is 2a. And we have energy criteria. So this is Graves. So this is Professor Graves is a talented professor in 1920s. That's almost 100 years ago. And he proposed that this is energy criteria, and he used this is the G. This is the G, and G equals pi and sigma squared multiplied by A. A is the half of the whole crack of the central crack, and the Young's modulus. And so then we compare this G and with this GC. And GC, whenever you see the subscript C, it means that it is a material parameter. So this is material resistance to fracture. So this GC can be obtained and based on the relevant ASTM procedure policies. Okay, so which policy? And you need to check online. So this may induce the surface energy, plastic work, and other types of energy dissipation associated with propagating crack. So this is the surface energy, plastic work, other types of energy dissipation, and we have energy dissipation there. So G is denoted as energy release rate. So energy release rate, based on this energy criteria, energy release rate is the driving force for the crack. Whenever we want to predict if this crack is stable or this crack tends to propagate, and we just calculate this G, and then we compare this G and with respect to GC, which is a constant parameter, and once you select a material. So if G is greater than GC, and the crack is going to grow. And if G is greater than GC, crack is going to grow. And based on this equation for the critical moment, and we have, here is the typo. GC equals pi sigma F ACE. And the sigma F is a failure stress. Can you write down, guys? right? So sigma, this should be a sigma f based on this equation is based on this equation, and sigma f is this sigma f is a failure stress, is a critical stress that for this AC, for this crack tip, for this crack, and you can, and so this is the energy release rate, and energy release rate can be equal to the GC. So this is a critical the condition, and sigma 1, the sigma f, we denote this one as sigma f. So GC is independent, and AC is a critical crack length. AC is a critical crack length, and so this is of the is independent of the size and geometry of the cracked body. You should know that GC is only dependent upon the material and what the material you are using. It has nothing to do with the crack length, and it has nothing to do with the geometry. Otherwise, so this is unpredictable. And then we talk about the stress intensity factor. And so you can see stress intensity factor and the energy release rate, actually they are related and using one equation, this equation. And energy stress intensity factor here, what is the function of stress intensity factor? And we can use stress intensity factor to describe as a stress field in front of the crack tip. For example, here is a crack. This is a crack. So this is a crack tip. This is a crack tip. And if we establish XY coordinate system, X and Y, for any given point of interest, and we have a polar coordinates, right? Polar coordinate means how far this guy is from the crack tip and what is angle. And we have R and theta. This is R and theta. So this is sigma ij. This ij means 1, 2, 3. Okay, this is the stress components. And sigma ij can be denoted as Ki, and 2 pi square. This is the denominator, and here is a function Ij theta. Ij theta is a function of theta. So you can see here. Okay, so if the Ki, okay, if the Ki equals Kic, and Kic is material parameter, and it's very similar to GC, and Ki is dependent upon crack length and also loading. The Ki dependent upon crack length and loading conditions. But Kic is a material parameter. It is not same. Okay, this is as the GC. It is a material parameter. So as also we can see, this one is driving force for the fracture. So Ki is completely characterizes crack tip conditions in a linear elastic material. This Ki is as long as the loading conditions and also the crack length, everything is the same. Ki is constant, and we can use this equation to describe the stress distribution in the neighborhood of the crack tip. So Kic, and Kic is size independent material property of the cracked body, as I said, and Kic is very similar to GC. They are material parameters. Once you select a material, GC and Kic, and they are determined and they are fixed. If we want to use material, if we want to use another number of Kic or GC, you need to select the new material. And then, so the stress intensity factor and energy release rate, they are related. And we have one equation to relate this energy release rate, and this is the stress intensity factor. They are equivalent for linear elastic material. And why we say for linear elastic material? For plastic material, plastic linear fracture material, and they are different. Right? Can you guys draw down? And so this equation is only valid for linear elastic material. If the material contains plasticity, and we have another story. You can see very beautifully related. G is related to Ki square using these Young's models. The fracture mechanics often plays a role in live prediction of components that are subject to time-dependent crack and growth mechanism. For example, fatigue or stress corrosion, the cracking. So we will talk about this one later. Here is a fatigue. And have you guys ever heard of fatigue? You heard of fatigue, right? And what is a fatigue? And fatigue means that even under some very, very low loading conditions, if we repeat this loading, the loading condition repeat as the time goes, as the number of cycles increases. So this even though the loading is very, very low, but and still can cause trouble because this is repeated cycle. And so fatigue, and this fatigue, this A, you can see A here is a crack length, and this capital N is a number of cycles. So dA dN, that means the derivative of A with respect to number of cycles can be written as C multiplied by delta K M. So who have taken the computer-aided engineering with me? Please raise your hands. Computer-aided engineering? You took, right? So we know that, we know this fatigue, right? You still remember? And for machine design, and who have taken machine design with me? In machine design, we talk about this one also. You still remember? Machine design. So delta K, what is the delta K? It's the range of the stress intensity factor because the loading is competed. Its loading is a cyclic loading on high, low, high, low, high, low. Because high, low, and we will have the stress intensity will have a range. And so we use this equation to describe the prediction, the propagation of the crack. And so this you can see this N and can be written as A0 AF 1 over C delta K M dA. So this A0 is initial crack length and AF is a final crack length. So here is this is called the stress intensity factor approach. And now the second approach is a stress and Einstein diagram. And you still remember as the Einstein diagram, right? S is the stress, N is number of cycles. And for all this is materials that contain the iron, and Einstein diagram is a straight line. I think I remind you guys, right? The straight line go this way, just like a knee. So here is two approaches. We talk about these two approaches in machine design. One is based on this is a stress intensity factor. One is based upon this Einstein diagram. So this is, and we will talk about this one later in our fracture mechanics. Any questions regarding these equations and also energy release rate and this stress intensity factor? Any questions? No question? We move on to the next one. So here is family tree of the fracture mechanics. So the basics is the linear elastic fracture mechanics. So in this branch, the plasticity is ignored, or the plasticity is very, very small and we just ignore it. And so second one is elastic plastic fracture mechanics. And then after this one, and there are dynamic fracture mechanics, and viscoelastic fracture mechanics, and viscoplastic fracture mechanics. There are several branches, and these are three branches, and they are time dependent, and therefore time dependent materials. So for our case, we focus on the linear fracture mechanics and this nonlinear fracture mechanics. So here, so look at it here. This is the effect of fracture toughness on the governing failure mechanism. So here is LEFM. So this is a brittle fracture. You can see we have brittle fracture. And so here nonlinear fracture mechanics, and this is becomes a curve and from the straight line. And here after this, we have limited load analysis. And when we reach it here, and it is collapses. And so this is hypothesized is fracture toughness, KIC, and so here is the failure stress. And the KIC, the lower the KIC, and the better we can use LEFM and to describe this is the fracture, the behavior of material. So here is a typical fracture behavior of selected material. It dependent upon the material parameter, material this is a properties. For example, high strength steel and high strength steel is very brittle. That's the reason we can just use linear and linear elastic fracture mechanics and will be good enough. For low and medium strength steel, because there is decent the plastic deformation involved, and so we need to use elastic plastic or full plastic fracture mechanics. It totally dependent upon the material properties. You can see for this monolithic ceramic, it is very brittle, and so we can use linear elastic. Ceramic composites also very brittle, and we use linear elastic fracture mechanics to describe it. It's very good. For all other materials, the linear fracture mechanics itself is not enough, and we need to use other the fracture mechanics. Any questions? So, any questions? No question, and then we talk about dimensional analysis. And have you guys ever heard of this is a dimensional analysis? And so we will have the homework, get homework, and use the dimensional analysis. And what is a dimensional analysis? And all physical laws are dimensionally homogeneous. All physical laws are dimensionally homogeneous. So we will talk about the Buckingham, the pi theorem, or the dimensionless theorem. And what is a dimensionless analysis? Dimensionless analysis means that suppose we want to determine the relationship between a bunch of input variables and a bunch of output variables. And we need to determine which of these input variables plays an important role and which is not playing an important role. And we can do this is the dimensional analysis. So we also call the Buckingham analysis, pi theorem. Are you guys following me? It's kind of boring, right? It's boring. We will have homework very soon. So what is the dimensional analysis? So for example, these variables. Variables we have U, W1, W2, and Wn. Right? So these are variables, and can be input variables, can be output variables, and dimensions. Actually, dimensions is the unit. Write down, guys. Dimensions here, I'm talking about the units. For example, this guy's unit. I just use this is a square bracket U to denote this guy's unit, and so on and so forth for Wn, and the Wn's unit has Wn the square bracket. So all the variables they have units, right, guys? If this guy is does not have unit, we call this guy is either a dimensionless quantity or a ratio. Make sense, guys? Okay, without loss of generality, we assume all of these guys they have their own units. If this guy does not have any unit, that's good. That is good. Problems become easier. Okay? So first, you can see the U is the output. But here we have one output. U is the output, and U is a function of all these independent variables on W1 and Wn. And W1 through Wn, they are input variables, and U is output variables. And we want to determine the relationship. We want to determine the function of U with this in terms of W1, W2, and Wn. And how can we do that? So this is after we finish this dimensional analysis and how to determine the relationship between output and input variables will become very, very easy. Okay? You can see first step, we need to find m fundamental dimensional units and fundamental dimensional units. And we write this one FDU prime S. Right? So these are fundamental dimensional units. What does that mean? Fundamental dimensional units, we have several, and we have length, and we have time, and we have mass. You guys agree? Can you think about another one that is fundamental, that is not related to any other things? So suppose, okay, just for example, we have L1, L2, Lm. So we have m equals 3 here. We have length, time, mass. So these are 3 fundamental units. And then we identify m primary variables that contain all FDUS. Suppose without loss of generality, we think W1, W2 through Wm, and they are primary. This is the primary variables that contain all these 3. This is the primary variable, primary fundamental dimensional units. W1, W2, W3, and one is for length, one is for time, and the third one is mass. And for all other independent variables, and we call secondary, so number of these parameters is the total n minus the m. Question, guys? Question? Okay, first we identify this is m primary. This is the variables that contain the fundamental dimensions. And then we have secondary n minus 1, the variables. Right? So this is n minus 1 variables can be written by using this is 3 fundamental variables. Do you guys agree? Do you guys agree? Do you guys agree? I have fundamental, the variables, have fundamental units. And then for all other variables, I can write all other variables by some equations using my fundamental units. Right? Okay, because here. So W without loss of generality, we say Wm plus J. This J is from 1 to n minus J. So you can see this guy can be written as W1, W2, and Wm. And I have this dot. Dot means multiplication. And then I just give exponent. So this exponent dependent upon which variable you are talking about. We have Am plus J1, Am plus J2, Am plus Jm. So this is 1 for this from the fundamental unit 1. And this 2 is fundamental unit 2. And so this is M is a fundamental unit M. Are you okay with this, guys? Are you okay? Okay, so then we define new dimensionless quantities. So new dimensionless quantities on pi j. And pi j is defined as Wmj divided by the units of this mj. Are you okay with this step? So this is my Wmj. So this is the denominator is the unit of this variable. And then this guy pi j, this guy will become a dimensionless. Do you guys agree? I hope.
What is a dimensionless like quantity?
The dimension is this guy is just a ratio, just as a string.
Yeah.
A string, a stress has a unit gigapascal, megapascal, but string does not have, right? You guys agree? The string actually is a ratio of the deflection of this is a specimen divided by original length. Length divided by length, right? Even though this length is different unit, micron, one is micrometer, one is millimeter, but actually you can just unify them using meter. Agree? Here is the same thing. And W M plus J, and so this guy has some unit. And then here, so this is unit. This guy has the same unit as this one. If I divide them, and this unit disappear. Right? As a result, this guy is a ratio. Now you can see, and pi j is a ratio. It is not a variable that has a specific the unit. The same thing, the u, the output, u divided by u unit. So this guy, we use the pi, right? So this is pi, and so this one is the function of pi 1, pi 2 through pi n minus 1, n minus I. So you can see, so this is u divided by square root u is a dimensionless ratio. So this guy is a function of all these n minus n ratios. Right? So that's the reason this is called dimensionless analysis. So you can use this dimensionless analysis for any physical phenomenon to determine the relationship between input variables and output variables. Follow me?
Yeah, we did this in fluids
You did this in fluids? Or when this semester?
last semester.
Or last semester? Okay, good. It may be different professors, they have different the teaching, right? So this one is based on our fraction mechanics textbook. Questions so far? No question? And I think you are looking for examples, right? I have examples. When I was a student, when my professor taught me some very confusing equations, then I look forward to how to use this equation to solve problems. So for this one, I'm going to give you one example. For this is example. So here is the infinite plate, the half plate. Half means, so this is a straight line. But here for all other dimensions, and they are infinite. And we have sigma and infinite. This is the stress. Also, this is sigma. The crack length is given, and for any generic point in the neighborhood of crack tip for this point, we have r and we have theta. And then the sigma ij, okay, sigma ij, I want to determine the relationship between sigma ij and all other factors. So sigma ij can be written as a function f1, right? A function of I do not know what kind of function it is. I do not know. But the sigma definitely it is related to sigma of infinity, crack length, Young's modulus, and how stiff the material is, Poisson's ratio, and for this given point, definitely the r, right? The polar coordinate, how far this point is from this is gravity, and then theta orientation. So I know this one, and then I do this is dimensionless analysis based on the procedure we just talked about. And first, I will take a look at these units of what this is into the variables. You can see sigma infinity and Young's modulus, and they have stress dimensions. Do you guys agree? They have stress units, they are stress dimensions. And gamma is a nu and theta, and they are dimensionless. Do you guys agree? Nu is the ratio, Poisson's ratio, and theta is just angle. It does not have any physical unit. And A and R, A is the crack length, R is the distance between the generating point and to the crack tip is R. And so this is length. You guys agree? Okay. So we can see here. So sigma m, and you can use sigma infinity. And sigma infinity and n can be the primary quantities. Do you guys agree? Why I can use sigma n, sigma infinity and a as the primary quantity? Because E has the same unit as sigma infinity. R has the same unit as the crack length. And nu and theta, they are dimensionless. Are you guys okay? And then sigma infinity and n can be primary and quantities. And then we use this equation, guys. You can see? Look at this one. Look at what I'm pointing at now. We can use this equation, okay? So this is sigma ij divided by sigma infinity equals a function. I just change from the f lowercase f1 to capital F1. Because when you do some math manipulation, so the actual function will be changed. You guys agree? Okay, that's the reason I change it to the capital F, F1. So this is sigma m disappeared and a disappeared because they are primary units, fundamental units. So these two guys are disappearing. So E nu and E, I can just use the sigma infinity to divide E. I use A to divide R. And then I have this guy becomes dimensionless and this guy becomes dimensionless. For nu and theta, I do not need to do anything. Look at me. Are you okay? Let's come back. Let's say sigma. This is sigma infinity. And this is A. And here, look at this equation. How can I do that? I can just use this one. So this is the unit of sigma infinity. And this is the unit of the A, right? Right, guys? So this exponent, you can see the exponent. This exponent is dependent upon what variable you are talking about. And for the sigma, and for the Young's modulus, I just divide Young's modulus using this one. And sigma power 1, A power 0. A power 0 equals 1. 1, right? So this one equals 1. Then that's the reason I have E divided by sigma here. E divided by sigma infinity. The same thing for the R. So this R, okay? So this R can also be written as sigma something and then A something. So here I just put 0 here, and here I just put 1. So this one disappeared. Oh no, so not 0, it's 1. If the 0 is it blows up, it's not 0. You understand? And for gamma and theta, guys, for gamma and theta, I can just put these two exponents equal 0. Because gamma theta, they are dimensionless already. Right? You understand? Michael, are you okay? Okay. So you can see, so this is my dimensionless analysis for this one, for this the half the cracked body with infinity. This is the dimension with infinity is infinity. So then I look at another case. So this is half crack, but so this is here is the distance W. We have the width. Okay, but this one we do not have width. It is infinity in the horizontal direction also. Here we have W here, and we have infinity sigma infinity. And so this one edge crack in a finite width elastic plate can be written as sigma ij f2 sigma infinity crack length Young's modulus Poisson's ratio, and R is the distance between the point of interest to the crack tip, and theta is the orientation of this the point, and W is the width. W is the width of the plate. And we can also see that sigma infinity and A, they can be used as primary quantities, because all other variables can be written in terms of zone. And that's the reason we can have so this equation, sigma ij divided sigma infinity equals F2, capital F2, E divided by sigma infinity nu R A theta WA. W is the width, right? The width is the length. And WA say R nu E, but sigma infinity and A will be taken out, because these two guys have been used as the primary unknown. This is a primary infinity, primary is unit. Yes, are you following me? Okay. The last example is this one. Okay, this one is the edge crack with a plastic zone as the crack tip. It's still edge crack, but this time we have plastic zone. It's a plastic zone in front of it. Plastic zone. So suppose crack length, and we have the radius of the plastic zone Ry, and also sigma y. Sigma y is yield strength. So the sigma ij can be written as C is a function of sigma infinity, crack length, Young's modulus, Poisson's ratio, and the distance between the point of interest to the crack tip, and theta is orientation. W is width. Ry is the distance. Is the size of the plastic zone, and sigma y is the yield strength. So these two guys, they are related to plastic deformation, and sigma y is the yield strength. And these, as I said, these two guys are related to the plastic deformation. So we can see, okay, sigma infinity, Young's modulus, sigma y, and these three guys, they have the stress dimension. And nu and theta, their dimension is A, crack length, R, the distance between the point of interest to the crack tip, Ry is the size of the plastic zone. So these three guys, they have length dimension. Right? They have length dimension. As a result, I just use these sigma infinity and this A, and I use these two guys as the primary units, and based on what I just talked about, very similar to this one, I just dimensionalize all of these variables. Also, I dimensionalize dimension is make this sigma ij dimension is also using the sigma ij divided by sigma infinity. Right? Questions so far? No question? So no question, and then we move on to next the next one. We just do as much as we can. Right? So This is linear elastic fracture mechanics. So we just do this one as much as we can. We cannot promise we can finish. We only have 9 minutes now. This Friday I can finish this one and also the fourth lecture. I want to go through. So this linear elastic fracture mechanics. So we suppose we have 2 atoms here. So these 2 atoms, and they have a space x0. X0 is called equilibrium and spacing between these 2 atoms. And why it stays equilibrium spacing? Because at this instant, excuse me, when the distance between these 2 guys equals x0, so this guy have a minimum potential energy. Right? Minimum potential energy is unstable. However, if you either press it and push them together or pull them apart from each other, and you are increasing the potential energy. So this is a bound energy. So we have a bound energy. Bound energy, this is B means bound. Bound energy means that suppose you have a load here, and you just move this. This is one of these atoms, and from this is equilibrium spacing x0 to infinity. So that if you want to do this, and what amount of energy you are spending, that is called EB. Right? So this is called bound energy. And P is the derivative of Young's modulus and over this dx, and P is applied force. We have a theoretical cohesive strength and theoretical cohesive strength and sigma c. So this is defined as PC divided by x0 square. X0 is a spacing equilibrium, and PC equals EX0 lambda divided by pi. So then we multiply by this guy by 1 over x0, we have this is sigma c, E lambda and pi x0. This is a lambda, okay? So this is a lambda. It's lambda from x0 and to here, this lambda. And usually the lambda is about 2x x0. This lambda. So this is one equation. And for here, you can see for here, so this one, if we have a straight line here, so this curve can be approximated using a sine function. And you can see the P can be written as a PC, and PC is a cohesive force from 0 and to the maximum point here, tension. So this one can be written as a sine function. And so here is a pi x is lambda. So we suppose this is x is very small. So if sine function is this is the independent variable is very small. So the sine value almost equals its original value. You understand, guys? One more time. Because if the x is very small, then pi x lambda almost equal to sine pi x over lambda. Right? We know that. And so that means if x is very small, and then x is about sine x. So P can be written as PC pi x lambda. And then we introduce the K, the constant, and K equals P, the force, divided by X, the deflection, and then this K can be written as PC multiplied by pi divided by lambda. Wait, and sigma C has the same magnitude as that of Young's modulus. And then we introduce a gamma S. The gamma S is a surface energy. And surface energy, it is the energy you need to spend to crack something per unit area. No? Okay, so this is called per unit area. The gamma S, right? And gamma S equals half F0 lambda PC. So this is PC sine divided by x0 squared dx. So why is the half here? Why is the half here, guys? Because we have two faces. Whenever you have a crack, and you have two crack faces. Do you guys agree? So that's the reason the gamma S we have 1 over lambda here. And then we just put in, this is because of PC, and this is the PC here, and we just plug in, and we can have this. And for this integration, I wrote down this how to do the integration here, and then we know how can we get this equation. Gamma S equals sigma C multiplied by lambda divided by pi. So this is equation 2. After we get this equation 2, we put the equation 1 here and into equation 2, and we can calculate the cohesive strength is sigma C. Right? Cohesive strength sigma C. It is the function of Young's modulus, and this is the surface energy along with the equilibrium spacing. So here is two important concepts. So PC is a cohesive force. It's a force. Force unit is Newton. And cohesive strength. So this cohesive strength, and this case unit is Pascal. What? Pascal or gigapascal, megapascal, kilopascal. So you should be very, very careful. So why actual strength is much lower than sigma C? So this sigma C, the theoretical sigma C is usually very, very huge. But it actually, in reality, the material's behavior is not that good. Why? Because we have a lot of defects in the material. But these defects just deteriorate the behavior of this material. Any questions so far? No questions? Then we talk about this is our first equation of stress concentration. And suppose we have, so this infinite plate, we have a central crack, and sigma is applied in the infinity place. This is proposed by Inglis, the Professor Inglis. And for elliptical hole, we have 2A, 2B. And sigma A, the stress intensity factor can be written as using this one, 1 plus 2A plus B. If the A, can see if the A is becoming bigger, and then we will have a sharp crack. What's the sharp crack? A sharp crack means that the distance between these two crack surfaces is relatively very small. Okay, so I'm going to stop here now, and it's Friday. I'm going to continue. If you have any questions, guys, feel free to see me here in the office hour. What? Or email me if you have questions. And please email me.
I started now.
And
Forgot.
you also-